Hey everybody, in this video we're going to continue to look at implicit differentiation. We're going to see how it relates to various applications, and we're looking at what's called related rates. So related rates are when you have one formula or one equation that's got multiple variables in it. So we know the volume of a cone. We can find it by if we have the height and we have the radius of the base of the cone, or the radius at any given height in the cone. So that will give us the actual volume for the cone. Now, if we want to find out if the cone is getting filled up with water or water is leaking out, and we want to see how fast or what the rate of change is with that at any given instant, we can find the derivative of this equation. So remember that differentiation refers to the rate of change at an instant. Differentiation refers to the rate of change at an instant. So what that means is, of course, that instant is going to be looking at time. So we're looking at what's happening at a specific moment in time. And we know that the radius, the height, and the volume, they're all going to be changing if this thing is getting filled with water or if it's leaking out water. Every single one of those things are going to be changing with that time as the volume changes. So what we need to keep in mind is that they will change with time, and that all changes are proportional and are related. Okay, so all of the changes that's happening between our radius, our height, and our volume are all going to be proportional and related, depending on how quickly or how slowly we're filling up this cone. So let's say we've got an empty cone and we're going to fill it up with water. So we've got a nice full cone, but the bottom springs a leak and it starts leaking out, but we're able to stop it at a specific point. Okay, so what are we going to do here? We're going to look at the height at the moment that we stopped it, and we'll also have to obviously see what the radius is if we want to know what the volume is of the cone, or how much water we have left in the cone. So we're going to look at this with relation to time. So looking at, as this water leaked out, what's happening at a specific moment in time when we stop that. Or maybe we just took a measurement at a specific moment in time and this thing is still leaking out. Either way, we're looking at the rate of change. So we have our volume equals pi over 3 r squared times h. And if we want to see what the instantaneous rate of change is, we're going to take the derivative with respect to time. Time being that instantaneous, or the instant, right? Instantaneous, we're talking about time. So we're taking the whole equation with respect to time. So we'll take a derivative of each one. But remember that if these variables don't match, we have to use implicit differentiation, or we have to use that modified chain rule. So the derivative of the volume with respect to time is going to equal pi over 3. Now remember, this is a constant, so nothing changes with pi over 3. And then we take the derivative with respect to time for our radius. So that's going to be 2r, and then with the chain rule, 2r times dr over dt. And now we have to look at the height, and that's to the first power, so the derivative of h with respect to time is going to be 1 times dh over dt. Okay, so now this is a fairly complex formula, but if we have some given information, it'll make things a little bit easier for us to find the instantaneous rate of change. So remember again that this is the volume is changing with time, the radius is changing with time, and the height is going to be changing with time, all with the same time value. Okay, so let's put some specifics in here. So let's say our radius is going to be 6 inches. And at that specific moment, we know that our height also equals 3 times our radius. Okay, so this is going to make things pretty easy. So if we want to find the volume of this, we're going to take pi over 3 times r squared times 3r, right? So we're just replacing h with 3r. We can do some simplifying and we get the volume is pi over 3 times 3r cubed, and do some more simplifying, get rid of those 3's, and we get the volume is pi r cubed. Now we said r is 6 inches, so we plug in our 6 and we get pi 6 cubed, which is 216 pi. Alright, so that's easy. That's how much water we have in the cone at that specific moment. So if we were able to stop the leakage, then we know that we've got a volume of 216 pi inches per inches squared. So if we look at what's happening, if this continues to leak out, then we are looking at the instantaneous rate of change, and we are going to be looking at when r is 6 and dr over dt equals 2. So that means the rate of change of the radius at a specific time is 2. Alright, so what we'll do is we'll take our modified formula, our volume of pi r cubed, and we'll take some implicit differentiation. So we'll take the derivative with respect to time for this function or this equation. So dv over dt equals 3 pi r squared dr dt. Now remember that 3 comes from the exponent of our radius, and then we take the derivative of that, so r cubed becomes 3r squared. The dr dt comes along for the ride. So now we just plug in our value for our r squared, which is 6 squared. Our dr dt is 2, and we can see that the rate of change, the instantaneous rate of change for our volume with respect to time is 6 squared times 2 times 3, which is 6, so 6 cubed, which is 216 pi inches squared per minute. So that's how we use implicit differentiation with what's called related rates. It's generally going to be looking at the derivative with respect to time, and then finding an instantaneous rate of change using that implicit differentiation to find a given value. So I hope this helps kind of see how some of this ties together, and good luck with the problems that you're working.